So we've been alluding some time now to the ultimate objective of inverting the analysis to recover the Mueller tensor elements. We're going to talk about how to actually do that in this next section. So if we take and vectorize the right part of this equation, we can, in order to generate the Stokes vector for the output, then it's given by this expression over here on the bottom, in the middle actually. So this is the vectorized form, so this is the ascending vectorization notation where the indices of the Mueller tensor are in ascending order, so 0, 0, 0, 0, 0, 1, 0, 0, 2, on up to 3, 3, 3. And so we can keep track of where they are in terms of the vector. And that's then given by this, that's related back to the Stokes vector for the output by a 4x4 identity matrix chronicled with the two driving fields transposed, the driving Stokes vectors transposed. And this is, again, it just drives straight from the vectorization discussion. This is a review. So we know from the discussion relating the laboratory frame to the local frame that we can substitute all of this in for the laboratory frame response. And here we're taking advantage of the fact that we're rotating the local reference frame relative to the laboratory frame to take advantage of local frame symmetry and populating the full set of 64 elements by the symmetry matrix from the smaller subset that are unique and non-zero. And the goal is to isolate and recover that unique non-zero subset using measurements of the Stokes vector as a function of the incident Stokes vector. All right. So goal is to isolate this given this for known those. So what we're going to do is actually, you can see immediately that if I have one Stokes vector, then I have 4 observables. And I've told you that even in the case of local uniaxial symmetry, we have 20 unknowns in the local frame Stokes tensor, local frame Mueller tensor in the most general case. That's clearly not enough observables to invert this problem and solve for the unknowns. So what do we do? Well, typically we do more than one measurement. So if we now consider a set of many measurements, let's say I have one measurement for the 0th measurement I make for a particular incident polarization state given by S omega chronicled with S omega. And then the second measurement indicated by the index 1, I have a different polarization state going in, and I have up to m different measurements for m different polarization states. I can stack all of those into a matrix. It'll be a 4 by m matrix. Now let's see, no, I take that back. That'll be a 4 by m. Hey, there it is, 4 by m matrix. So if we have a 4 by m matrix here, then what we'll end up with on the outside here is going to be a 4m. So because we're basically going to stack, we'll have one set of 4 parameters for the Stokes vector for 0, and then on top of that will be the next set for the Stokes vector for 1, and then on top of that the next set. So this is going to be a stack of 4m Stokes elements. Just each set of 4 we get from the Stokes measurement for a given incident polarization state. Hopefully that all makes sense. So this turns out to be a 4m by 20 matrix if I look at the entire set there. And as long as 4m is greater than 20, we have a hope of inverting this. And in that case, I'm just going to take this entire mess of things right here and call it T, because that's what we're going to do, just because I'm going to get really tired of rewriting the same group of things over and over again when I inverse and transpose and all that stuff. So we're just going to call it T, but we know everything in T, because we know the rotation matrix, we know the symmetry, and we know the incident polarization states we're putting in. We measure this, and we want to solve for that. So this is measured and then desired. And how do we get that? Well, this is a standard trick. If we want to isolate m sub l, we left multiply both sides by T transpose, and then left multiply again by the inverse of that term in brackets, and that gives us, that isolates m sub l local frame for us, and it allows us to solve for that in terms of the set of Stokes measurements. So this is a very general approach. As long as you have a sufficiently diverse set of polarization states going in that allows this matrix to be inverted, this matrix T to be inverted, then you can solve for the local frame Mueller tensor elements, irrespective of the local frame symmetry or even the presence or absence of local frame symmetry. It just takes, you can take advantage of the fact that if there is symmetry, that can be a smaller number of required measurements to be able to make. So that is a model-free description of polarization-dependent measurements and inversion of the local frame Mueller tensor based on just relying on symmetry alone, not considering any particular models for the local frame, for the depolarization that might be arising in SHG microscopy measurements. So the next step we'll do in the next 3 talks is consider 3 explicit models for depolarization and how they differ in terms of the experimental observables and, more importantly, the inversion of those observables to recover parameters related to the purely polarized local frame response.